we have been looking at the response of one dimensional continuous systems to initial conditions, and we have also looked at how this initial value problem can be recast as a forced vibration problem. Now, in this lecture and in the next few lectures, we are going to concentrate on the forced vibration analysis of continuous systems. Now, the question naturally arises, what are the sources of forcing, how or why we should study forcing. So, there are various reasons. For example, you can have a system with an actuation, say for example, for vibration control or for some other control. So, these actuators, they will excite the system, the modes of the system. Secondly, you can have fluid forcing, for example, a bridge or a high rise building that will be excited by the flowing wind. So, that provides forcing to structures. Then there are earthquakes and such natural sources of forcing. And finally, and very interestingly, forcing is also used for evaluation and testing of materials, for example, to detect flaws or phases or faults in a material or in a structure. So, from these considerations, it becomes important to analyze forced vibrations of systems. So, what are let us briefly look what are the ways of forcing a structure. So, you can have an actuator, you can just attach an actuator to on the structure and you can force it. You can force a structure like a string by bowing. So, in a violin, for example, you use a bow to excite the string by bowing, or you can you can hit the structure with an impact hammer, and that gives us impact or impulsive forcing to the structures. So, today we are going to look at forcing. We are going to start our discussions on forced vibrations of continuous systems, one dimensional continuous systems. So, let us consider a system. Let me first formulate the problem mathematically. So, for a system which can be put in this form, the kinds of system we have been discussing can be put in this form. So, here this represents a general forcing. Now, along with this, of course, you have the boundary conditions. Let us say 0, just to take an example, and you have initial conditions. So, this is the complete formulation of the forced dynamics of a system that can be represented by this differential equation. Now, this forcing term, as you can see, makes the equation of motion inhomogeneous. So, So, we no longer have W equal to 0, which is a trivial solution as a solution of this system. Now, there can be various kinds of forcing. You can have harmonic forcing, which is the most common kind of forcing, especially when we are evaluating or testing a structure. We provide harmonic forcing and we try to see the response of the structure, whether it matches with our expected response or not. So, this harmonic forcing is one of the very important types of forcing which we are going to look at. The second is the general forcing, which can be so in the harmonic forcing, for example, your q of x t can be, for example, q of x, capital Q of x times cosine of omega t, where omega is the forcing frequency. So, is the forcing circular frequency. So, here as you can see, this kind of forcing is separable in space and time, possibly separable. So, for example, one term, one frequency forcing like this. So, you have this as separated in space and time. Now, this is the amplitude function or the distribution of the force, and this is the temporal variation of the force. And any periodic forcing, as you know, can be represented as a series of harmonic forcing. So, if you know the solution for the harmonic forcing, then you can also find out the response to any periodic forcing. So, we can also deal with periodic forcing if we know how to find out the response to harmonic forcing. Now, when you have this non-separable, the space and the time part non-separable, and we are going to look at some examples of this forcing, and we have actually looked at one of the examples of general forcing when we write the initial value problem as a forced vibration problem, and we are going to discuss this shortly in the later lectures. So, today we are going to focus on the harmonic forcing. So, let me write the differential equation of motion as so the forcing that I discussed just now can be represented as a real part of this complex forcing term, where, as I mentioned, this is the force distribution function, this is the circular frequency of forcing, and this R represents the real part of this argument. Now, the solution, so this of course along with the boundary and the initial conditions will completely specify the forced vibration problem. Now, first we must write down the general solution of this differential equation. So, as you know, the general solution of such a differential equation can be written as the homogeneous solution, which means the solution with 0 forcing plus the particular solution, which is due to this forcing. So, this kind of a solution satisfies this differential equation, since the homogeneous solution will actually go to 0 once you substitute here, the particular solution will satisfy or equate the right hand side. So, the solution, the homogeneous solution, we have been looking at this homogeneous solution in the last few lectures. It can be represented as so, this is the homogeneous solution which is expanded in terms of the eigenfunctions of the corresponding eigenvalue problem. So, the eigenvalue problem was obtained by considering the homogeneous problem and searching for special solutions which are separated in space and time. So, from there we obtain these eigenfunctions, and we have been representing this solution for solving various kinds of problems, for example, the initial value problem. So, here again we come across this solution. So, this is the homogeneous solution and this is the particular solution. So, which satisfies or which meets this non-homogeneous term on the right hand side of the differential equation. Here this is the amplitude function. So, the amplitude function of the response. So, as you know that in an undamped system, the response is proportional to the to this harmonic time function. So, we have written this out as the real part of this amplitude times exponential I omega into t. Now, if we substitute this solution form in the equation of motion, the differential equation, then what we obtain. So, this term is going to go to 0. So, what remains comes from this term, and if you substitute this and make a little bit of simplification of the equation, then what you will obtain is so, this is the differential equation in x. So, this amplitude function, so capital X of the space coordinate small x. So, this is the differential equation that you obtain by substituting this solution in this equation of motion. Along with this, you also have the boundary conditions which this amplitude function must satisfy. This comes from the boundary conditions which we wrote out when we formulated the problem. So, what we obtain is a differential equation in this amplitude function with along with these boundary conditions. This specifies what is known as the boundary value problem. So, this is the boundary value problem corresponding to the amplitude function of the particular solution. So, we must solve this boundary value problem in order to solve this amplitude. Now, there can be various ways of solving this boundary value problem. One is the Eigenfunction expansion. Which is what we have been looking at in the past few lectures. This works on the premise or the fact that for self adjoint problems you have the eigenfunctions which are all real and which form a complete basis for the system. So, by complete basis I mean that any configuration or shape of the system can be represented in terms of these eigenfunctions, and we have been looking at this method in the past few lectures. So, you can represent any shape using these eigenfunctions, as we have done even for the homogeneous solution. So, this eigenfunction method is one of the methods that can be used to solve this boundary value problem. The other is the Green's function method. So, this is another method which we are going to look in the next lecture. So, today we are going to focus on this Eigenfunction expansion method for solving the boundary value problem. So, what we are going to So, in this eigenfunction expansion method, so we have our differential equation of the boundary value problem in this form. We are going to expand this solution, the general solution of this differential equation in terms of the eigenfunctions of the problem. So, these are the eigenfunctions of the problem which we have obtained previously by solving the homogeneous problem. So, if you substitute this expansion in the differential equation, then so here of course, these alpha k's are the are constants which are to be solved. So, so this is what we obtain. Now, this k is a linear differential operator. So, I can exchange the summation and the operator, and write it like this. Now, recall that the eigenvalue problem for this operator for this system read so, therefore, I can write the operator acting on the kth eigenfunction in this form. Now, this is what I am going to replace here. So, if I do that and simplify, so this is the equation that I obtain, which has these unknown coefficients alpha k, which I now need to solve. So, for this we can use the orthogonality condition for the eigenfunctions. So, let us see how we can solve using the orthogonality condition. So, the orthogonality condition of the eigen functions for the system that we are considering, that can be represented as So, for j not equal to k, we have this orthogonality condition. So, we sometimes denote this as the inner product like this. So, to solve these coefficients, what we can do is we can multiply both sides with the jth eigenfunction and integrate over the domain of the problem. So, we will say that we take inner product with the jth eigenfunction, and when we do that, what this does in effect, because of this orthogonality, only the jth term is filtered out. So, which means if we do this inner product, we take the inner product, then what we are going to obtain we are going to obtain this condition, and therefore, so that is the solution for alpha j. Now, I can take j from 1 to infinity and solve for all these alpha j's, but then this is contingent on the condition that the forcing frequency is not equal to any of the natural frequencies of the system. So, the circular forcing frequency is not equal to the circular natural frequency, any of the circular natural frequencies of the system. So, otherwise this alpha, the corresponding alpha j will go to infinity. So, you do not have a finite solution in that case. Now, let us look at the situation when. So, this completes our solution for the non-resonant case, as we may say. So, then finally, you can, as I had wrote, I will write this again. So, we have this solution, and the particular solution will be obtained as in this form. Now, this now has to be substituted in the complete solution, and remember that this homogeneous solution has these unknown constants C k and S k, which I had written just a few moments ago, those constants are to be determined from the initial conditions. So, we have to apply the initial conditions. To solve for the C k and S k in the homogeneous solution. So, that will complete the solution of the forced vibration problem. So, this part we have already done in a previous lecture, how to solve for these constants using initial conditions. So, we will not repeat that here again. Now, we are going to look into this condition, what happens if we have a resonant forcing. So, let us consider the case of resonant forcing. Let us assume that the forcing frequency is equal to one of the circular natural frequencies of the system, let us say the jth circular natural frequency. So, the forcing frequency is equal to the jth circular natural frequency of the system. In that case, our solution. So, let me write this equation once again. So, what we have is we have so, this is what we have. So, therefore, our particular solution we must now we cannot consider this. So, let me write down this particular solution as now we have been expanding this x, the amplitude function of the particular solution, in terms of the eigenfunctions. We will do that, but now because of this resonant forcing, and if you look at the solution that we just now derived, when omega, this capital omega equals omega j. So, this is going to be undefined. So, to prevent that, we are going to expand this as this for all k except k equal to j. So, the same expansion works for all the non resonant modes. For the resonant mode, we are going to consider or assume that this coefficient is now a function of time. So, this is going to be our expansion. Now, here So, this we have considered to be a function of time, as we do in for example, Frobenius method. So, variation of parameters. So, we assume that this is a function of time, and we substitute this expansion in here and the particular solution into our differential equation. Then for all the non-resonant modes, we have a way of solving, just as we discussed just now. For the resonant mode, we are going to obtain a differential equation corresponding to alpha j, which is obtained as if you substitute this and take inner product with w j, this is what you are going to obtain on account of orthogonality. Now, this differential equation, we know from our previous studies that this differential equation admits a solution of this type, where beta j is now a constant. It could be this, but then if when you substitute and evaluate, this vanishes. So, we have this only beta j, and beta j, if you substitute this solution form in here, then so this is the solution for beta j, and once you have this solution for alpha j, then you can substitute this in this expansion, and what you will obtain is so here, as you can see that this beta j is there is one 2I in the denominator. So, this complex, so it is imaginary, and when you substitute this and take the real part as here. So, when we substitute this whole expansion here and take the real part, what we are going to obtain finally upon simplification we obtain this sin omega j t when we take the real part, because of that I sitting in the denominator of beta j, and along with this we have the other terms. So, this completes the solution of the particular solution. Now, once again you have to add it with the homogeneous solution and use the initial conditions to solve the constants in the homogeneous solution. Now, here we see something interesting in this solution form. In the numerator of this term, so as usual the resonant mode, the amplitude of the resonant mode has an envelope which is linearly increasing with time. This is what we all know, that this is what happens at resonant. For the resonant mode, this is what happens. Now, in a continuous system like this, we have this integral in the sitting in the numerator of this resonant solution. Now, this integral in general will be non-zero, but then there are special instances where this will actually vanish. So, let us look at some situations. So, if you consider omega j to be the second natural frequency. So, omega the forcing frequency, the circular forcing frequency is equal to the second circular natural frequency of the system. In that case, as you know, for a string, let us say, so for a string, so for a taut string we have the eigenfunction sine of 2 pi x over L. So, this is the eigenfunction of the string, the second mode. And if we have a string which is being forced at the middle, so this let us say is the string, and suppose the forcing is of this form, is being applied at the middle. So, if you then substitute this, so q of x in this case is, and if you substitute these two expressions here, then you can easily see that this integral vanishes. So, if this integral vanishes, even though you are exciting at the second natural frequency of the string, so this is omega 2, capital omega is omega 2, the second mode will not show the resonant behavior, which means that because of this integral vanishing, so this term will drop out from the solution. So, the response of the system will still be finite. So, a force like this cannot excite this mode, it cannot excite this mode, because this forcing is at the node of that mode. So, this is one situation where there will not be any forcing. There can be other situations, for example, and one such example we are going to look into very shortly. So, what we see here is that in a continuous system, just forcing the system at a resonant frequency does not mean that you will observe a resonant solution. So, the location of the force is also important in these situations. Now, to look at what we have been doing, let us take an example. So, this is an example of a taut string. with uniform harmonic forcing. So, let me represent the situation that we have. So, this is the string and the forcing is a uniform. So, the distribution is uniform. So, the mathematical problem the differential equation, the boundary conditions. So, on the two ends. So, it is a fixed string. Now, we are going to look at solutions in this form. If you substitute this in the equation of motion, and removing the cosine omega t term for throughout, then we get this along with the boundary conditions. Now, we will simplify this a little bit by dividing the whole thing by the tension, and T over rho a is c square. So, I will write it like this. Now, this is the boundary value problem of our system, which we are going to now solve. So, as we have done, we know that the eigenfunctions of the Taut string are of this form. So, we are expanding in terms of these eigenfunctions, and when we substitute in here, and let me, so these steps are quite simple. Let me write out the solution. So, I substitute this in the differential equation and take inner product. With the jth eigenfunction. So, when I do that, I can obtain the solution of alpha j. These steps are straightforward. So, you obtain the solution for alpha j and you can put in any value of j and you can get this alpha j, and now you can substitute in the expansion to obtain the amplitude function. So, let me write out the particular solution then. So, cos of k pi minus 1 so that completes the particular solution. So, this is the particular solution of the problem. Now, this boundary value problem can also be solved exactly as this differential equation is straightforward, and the solution of this differential equation can be easily written as so this is the general solution. Now, see here in the previous solution we did not have to worry about the boundary conditions because we have expanded in terms of the eigenfunctions which already satisfy the boundary conditions, but now we have solved this exactly. Now, we have to satisfy these boundary conditions. So, if you solve for these constants d and e, you can easily obtain these constants which can be substituted here and you can once again get the particular solution, but now the particular solution is a closed form expression. So, this is the solution which is now in the closed form. So, we have kind of summed over all these terms to obtain this. Now, here one thing to note is you have this cos k pi minus 1. So, for even values of k, this is going to go to 0, this bracketed term is going to go to 0. So, therefore, you will have only odd, so only for k odd you will have non-zero coefficients. Now, in this figure, in this slide I have compared these solutions, the exact solution, the closed form solution with the series solution taking up to 3 terms. So, if you look at, so I have taken the forcing frequency very close to the first natural frequency of the string. So, it is 0.9 times the first natural frequency, and you can see that the exact solution and the series solution they match. Actually, I have plotted this series solution taking one term, another solution with 2 terms and another solution with 3 terms. Now, in the first plot they are indistinguishable with the exact solution. This is when you force it close to the second natural frequency. So, 2 times omega 1 is actually omega 2 for a string, as you know that they are integral multiples of the fundamental frequency. So, this is close to the second natural frequency, the forcing is close to the second natural frequency. This dashed curve is the series solution with only one term. So, you can see that this deviates considerably from the actual solution, while when you take 2 terms or 3 terms in the series, then they are matching quite nicely. This is when the forcing is close to the third natural frequency. You see the one term series solution is quite off, while when you consider 2 terms or 3 terms, then they are matching quite nicely with the exact solution. This is when you are forcing at the close to the fourth natural frequency. Again the one term solution is off. The 2 term solution is this blue solid line, the red line is the 3 term expansion series solution, and the exact solution is given by this black solid line. So, you can see that slowly as you increase the forcing frequency and consider higher modes or the higher natural frequencies, then 3 term the 2 term solution is now in error, the 3 term is still quite close, but as you will go to higher and higher you will have to take more and more terms in the series to get close to the exact solution. So, we see that the series solution actually converges onto the exact solution. So, let us look at what we have studied today. We have discussed the force vibration analysis of one dimensional continuous systems. We have looked at harmonic forcing and we have solved this problem using the eigenfunction expansion method. We are going to continue this discussion in the next lecture. We conclude this lecture.